Hi everyone and welcome back to HK Academy. In my last video I showed you how to simulate the closed loop voltage mode controlled buck converter using a Type 3 compensator in LTspice, and as I promised, today I'm showing you the real hardware demonstration. We will test the same control design on the TI F280049C LaunchPad together with the TI buck converter board, and you will see exactly how the converter behaves during load steps, just like in the simulation. The goal is not to show the full code implementation, that's part of my course, but rather to show you the practical behavior, the transient response, and how closely the real converter matches the LTspice model. On the screen, you can see two things. In the upper right corner, the complete hardware test bench, the F280049C LaunchPad, the TI buck converter board, the power supply, and the oscilloscope. In the bottom right corner, you will see the live oscilloscope window, where we will observe the output voltage, PWM signals, and load step waveform. Let me first quickly recap what each oscilloscope channel is connected to. Channel 1 and Channel 2 measure the complementary PWM signals that drive the synchronous buck MOSFETs. Channel 3 carries the PWM load step signal. When it is zero duty, only the 7.5 ohm load is connected. When it is 100% duty, the additional 2 ohm resistor is added in parallel. Channel 4 shows the output voltage of the buck converter. Our input voltage is set to 9 volt, and the digital control loop is running at 200 kilohertz using the discrete Type 3 compensator we implemented in previous lesson. We will now go step by step through startup, steady state, and load step behavior. Let's begin with the light load condition. Only the 7.5 ohm resistor is active. Channel 3 is at 0% duty, so only the base load is connected. Now I will flash the firmware and enter the debug mode, and then I will press here run. So from here we control two things via the live expression window. So here first we control the start and stop of the converter by setting the start converter flag. If we set this start converter flag to 1, this means our converter will start, and if we set to 0, our converter will stop. The next what we also do is inside the registers. Here I will enable just continuous refresh. Here for the PWM 2 signal, we directly set here the 0 or 100% duty cycle. So for 0% duty cycle, we are setting here 0, and for 100%, we are setting one count higher than the period, which is 40,000. So here should be 40,001, and then we will have really 100% duty cycle. Okay, so to measure the output voltage, here we will press the single, and then we will observe the startup procedure. We will start first with the basic load, which is 7.5 ohm. So let's now start the converter. If I press now 1, you can observe that our converter has started. You can now see the startup ramp on the channel 4. Notice that the rise to 2 volt take about 6 milliseconds. This is intentional and different from our LTspice simulation. So in LTspice simulation, we had approximately 2 milliseconds to 2.2 milliseconds. We apply this soft start ramp by increasing the reference gradually, so each PWM cycle, and this prevents overshoot and reduces stress on the output capacitor, and this is a common practice in digital control. So the approximately 6 millisecond startup time is expected and correct, what you can observe here. And here you also observe that there is no overshoot in our case. Okay, next let's test our converter in the case where we have the full load. So when we add the additional 2 ohm in the parallel to our basic load, first I will stop the converter, and then we will set our duty cycle to be 100%. And now we can start our converter again. And now you can also observe that we have the same startup procedure. The converter ramps up smoothly again, the same 6 milliseconds of start, and stabilizes at 2 volts even under the heavier load. Exactly what we expect from a stable Type 3 loop. You can also observe the current consumption on our DC supply. So now it is around 0.31 amps, and previously it was less than that, which confirms that we now have a different load. And you can also observe the channel number 3, which is now high. In the previous case was low, and this indicates that our load step PWM is set to 100% duty cycle. Next, I will switch the oscilloscope to the run mode now. And then we will reduce here time base to maybe 2 microseconds. And then we will set our trigger to be channel number 2. So on the channels 1 and 2, you can now clearly see the complementary switching, accurate 200 kilohertz period, and the 200 nanoseconds dead time we configured in the EPVM module. Channel 4 is the output voltage, and this stays right at 2 volt DC, as you can see. And this confirms that the compensator output and the PWM update logic are functioning correctly at the full speed. And here we can confirm that duty is approximately 24%, and we have 200 kilohertz switching frequency, and our average value from our output voltage is approximately 2 volts. Now that we have inspected the PWM signals and verified the steady state operation, I will remove the test bench view and the oscilloscope window from the screen. For the next part of the demonstration, we will focus only on the signals that matter for transient analysis, the output voltage, and the PWM load step trigger. This gives us a clean and uncluttered view, so we can clearly observe the undershoot, overshoot, and settling behavior. All right, here is a prepared oscilloscope setup for the transient test. So let's now begin with the DC coupling on the output voltage. First, I will flash again. Then we will just start the converter. Now it starts only with the basic load, and you can observe it is already in a steady state. So we have approximately 2 volts on the output. And now we will first hit here the single, and then we will do the load step. And now here you can observe the small dip, and after the small dip and settling time, we have the steady state again, and the channel 3 is showing us when we applied the load step. So from the basic load, we hit the heavier load. And then we can try again, but now in other direction. So now I will just set duty cycle to 0. And now you can observe the smaller overshoot here. And after the some small time, settling time, we are again in a steady state. Let's now first switch to the AC coupling so that we can actually see more detail this transient response, because now it looks very small, but we want to see more details. And I will also remove and set here 100 millivolts scaling, and then we can try to do step again. And now here you can observe what is the step, and we can see it's approximately 80 to 100 millivolts step, and the settling time is in a range something like 200 microseconds. Let's now try other direction, and here also you can observe that we have now a smaller overshoot compared to the undershoot. It's in a range of 60 to 80 millivolts, and the settling time is maybe a little bit longer, but it is very close to the 200 microseconds. If you want to try this example yourself, you can download the full C2000 project, including the source code and documentation, completely free from HK Academy. You will find the link in the description below. And if you would like a deeper explanation of the Type 3 compensator we used here, including the theory, the analytic derivation, the simulations, and the full digital implementation on C2000, make sure to check out my new Type 3 compensator course on HK Academy. For a complete step-by-step workflow of designing voltage mode control loops, placing poles and zeros based on crossover frequency and phase margin, and implementing everything inside C2000 hardware abstraction layer, the buck converter voltage mode control course is coming very soon. Thanks for watching, and see you in the next video.